Recording in progress.
Right. Today's lecture is going to be relatively short. We're just going to finish Bode plots. We're going to continue chapter 10 on Monday. So I'm currently typing up the rest of chapter 10, which is going to be Nyquist stability criterion. I actually have not taught that since for the last 2 years because I didn't see the need, but then I actually think there might be some relevance to it. So I'll be covering that this year. But I'm currently working on the lectures for that. So we're just going to wrap this up, probably just take 20 to 30 minutes, and we'll just call it a early Thursday. Are there any questions? And then maybe afterwards you can come pick up your midterm too. I also have midterm 1 if you haven't picked it up yet. And yeah, if you're online or you are not able to come in today, I'll have the exams on Monday for you to pick up as well. But if you did not, that's okay. I'm going to scan them all tomorrow and send it to you on Canvas for whoever has not picked theirs up. Maybe before we go to the lecture. So I have uploaded the rubric right here. So you can just use this as a reference point for grading your exams for problems 1 through 3. And then here are the solutions. I only gave really the answer, but not the middle steps. So what you have to deduce is, I guess in the middle steps, you have to figure out where you went wrong, but then you have the answer as a reference if you did it right or not. And all this is these are exam problems. They're not like homework problems where they're very like you need a calculator, except maybe for part B. And you've done all of these before, but now because it's on exam, it should be more easy. So use that, correct your exams. Shouldn't take too long. I hope it should take less than an hour to correct it. And then just submit it on here. You should be able to submit yeah. Submit your solutions or submit your grading and your corrections. And then homework 8 is going to be postponed, like I said. But I initially took off homework 8, but I think what we'll do is I'll leave it up on here just for now. This is the old version. So if you do these problems, that's fine because I'm going to be adding more problems on top of that, which will be due December 5th. So by next week, I'll add new problems to it and update this version. Okay, so back to the lecture. So yesterday we went over this example of drawing the Bode plots of the system s plus 10 squared divided by s plus 10 times s plus 10 to the fourth power. And you can see that the final plot of the magnitude is just the sum of all of the change in magnitudes. And then the angle is the sum of all the angle asymptotes. And that's represented in orange. If you look in this system, if we were to just look at it immediately, we can see that the system is always attenuating the input signal. So it's always going to be less than 1. Or yeah. Oh yeah, yeah, I can do that. Is that better? Oh yeah. Oh yeah. Yeah, there you go. Thanks for letting me know. Okay, so if we look at this, we can always see that this system is always attenuating the signal. So that means the output magnitude is always going to be smaller than the input magnitude, and that this system will always be in phase lag. Uh, the 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 phase of the system is always going to be lagging behind the input. So let's actually code this up in MATLAB. So I already have this up in MATLAB, and basically, actually, I don't have this in MATLAB. All right, let me just, that's gonna be for a later demo. So we're just going to do that example here where we have our transfer function and we have our uh, pole at minus 100, and then our pole at minus 1 and minus 10,000. So that's it. So you just put in your transfer function and then you put Bode, and then you can see that. There you go. That's the Bode plot. So it looks kind of similar to what we drew, where we had two flat areas. And then you can see the phase does this like little roller coaster. It doesn't quite hit zero again, like how we drew in the asymptotes, but that basically the idea is that the asymptotes of the total plot is going to be the bounds of our phase. It's going to be approximately where our phase will go. Now, if I were to instead replace one of the zeros with a different zero, so what we can do is this. If I were to now replace one of the Bode plots with a non-minimum phase zero, meaning a zero in the right half plane. So we have a minimum phase system. And then now we have a non-minimum phase system. You'll probably see that we'll see that the magnitude remains the same. So you see the blue and the red line are overlapping in the magnitude, but now you can see that the phase is different. So the starting angle is going to be at 180 degrees now. Right. So that's how you use the table as well for real zeros and poles. Now, if we were to deal with a system that has a pair of complex conjugate poles or zeros, I will show you what to do. So let's say we have a second order system that is underdamped. So this only occurs for underdamped systems because that's when we have complex conjugate poles and zeros. First thing we have to do is I'm going to set S is equal to J omega because we're trying to plot the Bode plot. So then we get G of J omega is equal to K times omega n squared divided by minus omega squared plus 2 zeta omega n omega times J plus omega n squared. And then we're going to divide everything by omega n squared. So now we get this term instead. Get K divided by 1 minus omega squared divided by omega n squared. So this is the real part plus 2 zeta omega over omega n times j. And this is the imaginary part of the problem of the denominator. So then now that we have this form, we can take the magnitude of it relatively easily, where we get magnitude of g of j omega is equal to, so here we're going to assume that k is going to be positive. Gain's always going to be positive. So then we just get k in the numerator because it's going to be the square root of k squared divided by square root of 1 minus omega squared omega n squared plus 2 zeta omega over omega n squared. And the phase of g of j omega is going to be this. Arctan of, so we're going to do the zeros first. It's going to be arctan of the angles of the zeros. So since we have no zeros, it's just 0 over k because there's no imaginary component, minus arctan of this, which is going to be the imaginary component, 2 zeta omega over omega n divided by 1 minus omega squared over omega n squared. And this is just equal to 0. Any questions? Okay, so that's the formulation for finding the magnitude and phase of complex conjugate poles. And if it was complex conjugate zeros, then it would just be the inverse. Or it would be something similar to this inverse here. The phase will be flipped as well. So we would have positive arctan of 2 zeta omega n divided by 1 minus omega squared n divided by omega n squared. Okay, so this is how you calculate it, but when we draw this on the Bode plot, there's actually something that you can do to kind of estimate what it's going to look like on the Bode plot without actually calculating this. So I'm going to write out our generalized second order underdamped system again. So with 2 poles. So we get k divided by s squared plus 2 zeta omega n s plus omega n squared. In this case here, I'm just going to let k equal, well, I'll just put k and omega n squared into the same constant. So let's let k equal to 10. Omega n is equal to 1. So actually, you know what? We're just going to have a 10 here instead. So we'll just let omega n is equal to 1. Zeta is equal to 1. This is a critically damped system because zeta is equal to 1, meaning we have 2 real repeated poles. That means that our equation here becomes g of s is equal to 10 over s squared plus 2s plus 1, which is factorizable into 10 over s plus 1 times s plus 1. All right, so this one's a very easy one to plot. And what I'm going to do is I am going to draw my decibel line, 0 decibel line right here on my magnitude plot. I'm going to find my break frequency, which is 1. And if we look at the starting point of 20 log of g of 0, we get 20 log of 10, which is equal to 20. So therefore, my starting point is going to be 20 decibels. So I have 20 decibels. Then I hit my break frequency. Now, we have 2 poles, each pole contributing to minus 20 poles per decade. So because of that, my break frequency is going to be decreasing at a slope of minus 40 decibels per decade. So if I were to look at this, this is minus 40 decibels per decade. I'll write that a little bit bigger. Are there any questions on that? How did I know where the break frequency was again? Yeah, so the break frequency is the frequency of it's the pole location. It's the magnitude of the pole location. So if we go back to yeah, so like in this example, the pole location's at minus A, but then we take the magnitude of minus A, it's just A. So the break frequency is at A. So here the break frequency is at minus 1, or it's at 1 because the pole's at minus 1. So then let's look at a different case. So that's when we have a critically damped system. Let's look at undamped system with the same natural frequency. So let's let K is equal to 10, and then omega n is equal to 1, and zeta is equal to 0. So I guess it's just omega n is equal to 1, zeta is equal to 0. So then when we look at this, and we get a purely oscillating system where we get 10 is equal to 10 over s squared plus 1, which is equal to 10 over s plus j and s minus j. Okay, and then this is where we see that we have issues because when we let g is equal to j omega, then we get 10 over 1 minus omega squared. So when we hit the break frequency of 1 again, then we get division by 0, and it goes to infinity. So we're going to get this, and then all of a sudden, we're going to get this sudden increase in magnitude going to infinity. Okay, so now let's look at the phase of these two systems. So when we're looking at the phase, I know that everything's going to be below 0 degrees. So I'm going to put my 0 degree line here. And then I'm going to have the frequencies line up. And for the phase, for the first system, where we have 2 repeated poles, maybe it should be consistent on the coloring here. I have 2 poles at -1, so at 10 times below the break frequency, I start having a change in phase of -45 degrees per decade per pole. But in this case, because there are 2 of them, I get -90 degrees per decade for 2 decades. Actually, I'm going to use the whole axis here. A little bit better for my drawing. So we're going to have -90 degrees. So then we're going to hit -90 degrees at the break frequency and stop decreasing at 180 degrees because of the 2 poles. And this is for the critically damped system. This is for zeta is equal to 1. And let me write that there. Zeta is equal to 1. For the phase, it's going to be 0 degrees. And then when we hit the break frequency, it's actually an instantaneous drop to -180 degrees, then it's flat. Any questions so far? All right. So then we're going to look at all the cases in between, or not all of them, but just a few cases in between. Then we look at, and choose a different color. This is orange. When we look at omega n is equal to 1, and then zeta is equal to 0.1. So a very, very underdamped system. It's almost no damping. Then we get g of s is equal to 10 over s squared plus 0.2 s plus 1. And basically, what I can say is, well, the magnitude is not going to get to infinity this time, but it's going to still have this bump. And then there's actually a way when you can predict when there will be a bump. Maybe it'll look like that. And converge towards this black line. And all right, so that's the magnitude. And for the phase, we're going to see that this very underdamped system is going to have a phase that's bounded between the red and black lines. black line meaning it's critically damped, and the red line meaning it's undamped. But because the damping ratio is so small, it's going to be closer to the undamped ratio, like the undamped line. So we can probably estimate that's going to look maybe something like this. You also indicate the red line is zeta is equal to 0. Okay, and then let's look at a condition where zeta is close to 1 then. So, and I'll give you the conditions on when there will be a bump and there won't be a bump. Then we get g of s is equal to 10 over s squared plus 1.8 s plus 1. And then it's going to just look more like the black line. We might get a slight bump there, but it's not resonance though. I'll give you the conditions for that. So then for the phase, we get something similar where it hugs closer to the black line than it will to the red line. And that's my phase plot. And that's zeta is equal to 0.9. So this bump here that you see is called resonance. So resonance, and it only occurs when the damping ratio is less than 1 over root 2. So then when there is a resonance, this peak here, which is called the resonance frequency, WR, is actually not the natural frequency. It's equal to omega n times 1 minus 2 zeta squared. So it's kind of similar to the damped frequency, but instead of it's a 2 instead of minus zeta squared. So if we look at this case, this is larger than 1 over root 2. So no resonance. And then this is less than 1 over root 2. So there is resonance. One thing to note about this is because there are two poles, we still have a contribution of minus 90 degrees per pole. So that's why we go to minus 180 degrees. It's for each conjugate pole. And then you can see that our asymptote line is minus 40 degrees per decade because the conjugate poles both have the same break frequency. So I don't really have a general rule or table for drawing complex conjugate poles. This is just how I would approach it. Any questions? All right, so we're almost done with this. We only got 5 pages left. I'm gonna just talk about gain margin and phase margin, and so this is the determining stability with Bode plots. So you can look at system stability when you look at the gain and phase margin. So it's easy to do a stability analysis on the open loop transfer function than the closed loop transfer function, because I think it's irrelevant now, but it's just because you don't have to find the closed loop poles. And if you can do the stability analysis on an open loop transfer function without needing to do the algebra of 1 plus g, um, then yeah, then that would work well. This is I don't know why system is unstable if 1 plus g is equal to 0. That's the definition of a pole. I need to look into this statement here. I haven't looked at it since last year. So basically, we have unstable conditions, and both must be met at the same frequency, where your gain is 1 and your phase is minus 180 degrees. And the way that looks like on a Bode plot is that if we were to look at our gain margin, if so what it means is if we were, I think the gain margins, if we look at here, that's the gain margin. We look at the 180 degree line or the minus 180 degree line, they're both the same. Then you look at the difference from the that point on the Bode plot on the magnitude plot to 0, and that's your gain margin. In this case, the gain margin is positive because we want to be below 1, a magnitude of 1 at the phase of 180 degrees. Think of it like if I was out of phase by 180 degrees for a mass spring system, then I'm adding energy into the system if my output is going to be larger than 1. So the output's going to be growing. The phase margin, it's a similar idea where if we look at the magnitude of 0 decibels, we want to look at how much phase we can lose before the system becomes unstable. In this case, this is also greater than 0 here. So phase margin is positive when we have when we have this margin here, and gain margin is positive when we're below the 0 line. So this defines our margins and how much gain and phase can our system handle before we become unstable. The reason why we want positive phase margin is because that's the amount of that phase margin is how much time delay our system can handle before becoming unstable. The gain margin is saying how much gain can we increase on that system before it also becomes unstable. How much gain can we increase to the open loop transfer function? So in MATLAB, we use the command margin. And when it plots your Bode, it'll plot your Bode plot and give you the gain and phase margins. And it's going to look at the point where it's going to, for the gain margin, it's going to look at 180 degrees and look at how much leeway you have before crossing the 0 decibel line. Phase margin is going to be looking at the 0 decibel line and seeing how much leeway you have between that and the minus 180 degree line before that's how they find their phase margin. So let me just show you that on MATLAB real quick. So here we just have an unstable open loop, and then you use the margin here, and you can see how you can look at the different margins for gain and phase margins. So maybe let's look at this first. So here they look at the gain margin here, where it looks at the 180 degree line, which is this first dotted vertical line, and then it just calculates how much gain we have before the system becomes unstable. Right here it says minus 5 decibel, meaning that we have to reduce the gain of the system by minus 5 decibels for the system to become stable again. meaning we have no margin left. We're already unstable. This phase margin here is we look at the 0 decibel crossover, and then we look at our phase, which is minus 180 degrees. Since we're below that line, it means we have to reduce the phase margin by 9.52 degrees, meaning that the system already has too much time delay. We need to reduce that time delay for the system to become stable. So these are the Bode plots of multiple gain and phase margins. I think figure 4 is of the same system, but then I reduced the gain to then meet the gain and phase margins again. Yeah, so I just reduced. Oh, that's a different system. Anyway, so I'll upload this code. I also actually have a code on the example we did on the pair of complex conjugate poles. So I guess you can briefly see that as well from the earlier example. Yeah, here's the example I just did earlier. The red line is our undamped system. The blue line is our critically damped system, and our orange line is a value in between damped, or it's an underdamped system. Okay, so that wraps up half of chapter 10. When we cover Nyquist stability criterion next class, but I guess some takeaways for this section is that for LTI systems, so linear time invariant systems, a sine input will result in a sine output with the same frequency, but likely different phase and magnitude, or phase and amplitude. Bode plots indicate the system's magnitude in phase as a function of frequency. The magnitude of Bode plots are typically in the log base 10 scale. This makes plotting Bode plots by hand easy. And then we talk about gain and phase margins, which indicate the amount of gain and phase the system can change at a specific frequency before the closed loop transfer function becomes unstable. And the gain and phase margins are found using the open loop transfer function, making analysis easy since the closed loop transfer function does not need to be calculated. This is specifically for negative unity feedback systems. I'm going to talk more about gain and phase margins with Nyquist stability criterion. I think it's more intuitive with that plot instead, which will be the final section that we're covering for this class. Schedule-wise, I think we should be able to finish all of the material by next Wednesday. And then I think the week after, I'll probably spend 2 days reviewing, like we're recapping the whole class for the final. And then maybe a day will be spent on a little bit of extension of like what's beyond chapter 10. Like I won't test you on that material. And then maybe a little bit insight on the classes that this kind of, if you want to go down the controls route, like what the classes like what options are available for you through the mechanical engineering department. Maybe that'll help with class selections. All right, thanks. And I will see you all on Monday.